And then she said that if I learn all of class, then I can do it again. So you gotta pay very good. So I have to pay attention.
All right. Here we go.
Yeah, guys, listen up. I'm Brad. Wait, Bradley, stop it. Bradley's at Northwestern.
All right, so we've got a mass. We have a rope with length L, mass M, uniformly dense. We're going to set up an integral to figure out the work done to pull up a rope onto the ledge at a constant speed if the front edge was just at the top of the ledge. We're ignoring friction. Okay, so the rope was dangling over, and then we're like pulling this up at a constant speed. Okay, good with that? Trying to find the work. So we know that work is equal to the integral of force as a function of position times a small infinitesimal change in distance. We're going to integrate that. What do you think our limits of integration might be? Start square and go to. Okay, we're going to pull it from 0 to L. Good with that? Okay. Now, the force that we need to pull is going to be equal to
You need to give her 2 put-ups.
There's a thing sticking out of the top.
okay.
We're learning.
We're focused.
I want to jump rope. Danielle. Oh, I just. Emma, I'm sorry you did that. DKC, you better do this.
All right.
I agree. No one listened to anything you said for the rest of the hour. Throw him down the stairwell.
We don't have to throw him down the stairwell. All right. Yes.
I'm your girl.
Hey. All right. All right.
I'm sorry, Brad.
Daniel, learn from your mistakes.
Get away.
No one likes you.
This is why you just assume no one.
All right. Here we go. The force. This might be good essay material right here.
You can get right out of being a boy.
I made fun of go. I didn't even say anything.
Okay, the force is going to be equal to the force of gravity hanging off of this.
Yes.
Is everybody okay with that?
Yes.
Okay. Is that a constant force? No. Okay. So we've got this. I'm going to say lowercase m for the mass of the suspended part. I'm going to say lowercase l for the length of the lower part. You all right with that? Okay. Now, problem with this is I can't integrate this because mass is changing. Okay, that's not a constant thing. I can't integrate that. So I'm like, so this is where you bring in this linearly dense, because uniformly dense. Okay, so you have mass over length. This is the entire mass over the entire length. That's why we use capital. Okay, and then this is also equal to the ratio of the suspended part Okay, which is also that. It's all the same ratio. It's all the same linear density. Okay. Now I've got more up there than I need for this problem, but I just wanted to like highlight that. Okay. So I need to make an expression for mass. Actually, can we do this? I'm going to modify this. Instead of dx, let's use dl.
Well, you should probably change the above. So right, not.
It's okay. You all right with that? Okay. So I need to get mass in terms of length. So uh, I'm going to take this right here. I'm not going to worry about that. So we got the whole mass over the whole length times just the section that's suspended. Okay. And then I'm going to substitute that in. Okay. So now this agrees. This agrees. They all have the same units. So now I can integrate. So I'm going to bring out everything that's constant. So I've got a constant total mass, constant total length, got a constant acceleration of gravity. I'm integrating L dl from 0 to capital L and find that to be 1/2 L squared minus 0, which is 1/2 mg L.
That kind of makes sense. If you think about it in terms of mechanical energy, you'd probably get
So
that.
if it's a, your answer. Oh, gee, like you couldn't include a variable that you defined.
If it's constant speed, there's no change in it.
Okay, good with that? Okay, now conceptually, so here's the entire length. Conceptually, the reason why that works is because what we're looking at here, the center of mass, would be located at half the distance. And we're lifting that from this height to this height, which would be half the length. You good with that? Okay.
You could have also just done this in terms of mechanical energy, since it's constant speed, so we know that kinetic energy, well, the change in kinetic energy is 0, so.
How does this work with changes?
That would, yep, sure can. You, so you would have, I would say, have a change in force, which would cause a change in, like if you'd pull it up with a force that was defined as this, like it would be like x squared, then that would change the speed. They probably wouldn't give it to you in terms of like, and the speed's accelerating from this to this. They probably wouldn't say that. They'd just say the force isn't constrained to be this. This is a special case to make it move at a constant speed. They'd just say, here's the speed you're pulling it. It's increasing or decreasing. How much work or how fast is it going at the end? Okay. Adam, did you have a question? Okay. All right, good with that? So let's throw some friction in there.
Oh, I hate it.
So I'm going to let you chew on it. Just a little bit. Mhm.
Will you come here for a second? I want to know what I was thinking was valid. Okay, so I said that if this is NG. I did something like
Just on the horizontal part.
I substituted this
Yeah, friction is just on the horizontal part.
N for this times L. That's just not valid because we want to find it in terms of.
If they gave you, you're right. If they gave you an expression like they said, hey, here's lambda, this is the linear density, you can write it in terms of that. That would be valid. But
Okay. It's
Wait, the little m is the mass like vertical,
yeah,
but then when you need the mass on top. Oh, and mine's waiting. How do you?
okay, ready?
Why is it FG plus X? F minus.
Because your force is gravity's going against you and friction's going against you. Okay. So here we have gravity. We have an expression for gravity, but we also need an expression for the friction, which is
Why is it minus? It's supposed to be plus.
sorry. Yeah, thank you. Which is friction's only acting on this part, which is going to be m minus lowercase m.
Okay, I guess you could do that.
You right with that? Okay. So this is capital M minus lowercase m times g times coefficient of friction dl.
Because your hand's acting both against the friction
Yeah. The net force, the total force is 0. So you have friction going against us. You also have friction going against us. Okay. So do what? I'm 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 adding them because both forces are opposing me pulling it up. Both are saying I don't want to go that way. So your free body, if I could draw a simple free body diagram, it would just be it'd be gravity going this way, and it would be friction going this way, and applied forces going this way. Okay with that? Okay. So I'm going to say mg coefficient minus, so I'm distributing this, and I have the same problem with lowercase m as I did here. So I'm going to say L capital M over capital L G coefficient DL.
Is this the type of thing we'll see with instead of solving for how much work is done, will it be like, here's the work done, here's the amount of energy used or whatever, and you have to set it up and calculate what the coefficient is?
So like what they'll do on a free response, they'll say part A, do this, part B, what's the coefficient, or like that, or like part A without any friction, part B with friction. What is that? Like, does that make, usually they build on it. Okay. So on here we can factor out an mg, and that's it. Right. Mg.
Why did you not erase the fraction bar? That's
It's fine.
So I got L over L plus mu minus L over L mu dl. So that's going to give me mg times L over 2 L minus coefficient L minus L squared 2 L. Yay. So that's going to give me, when I do 0, that's going to knock everything out. Okay, mg. Yep. 1/2. Well, yeah, I'll just do L. 2 minus coefficient times L.
yeah, it went from plus to minus.
It's scary because I don't have
Mu went from plus to minus.
Good catch. And then same thing. Oh, wait a minute, I need an mg. Sorry.
Just,
I know you're just gonna put parentheses to make just to show you that.
I got it, but I understand everything. I feel that. Well, I gotta find out.
What was your comment, Sam?
I said I'm understanding everything that you're doing on the board. I just don't think I can do it myself. Now we have to use all this information to build.
That is, you're about to. Okay, so
Wait, what?
did I get that?
It shouldn't be over 2L. The L should not be in the denominator. It should be in the numerator.
You're right.
What is it?
Good catch.
That's a good perspective.
All right. So this is the same expression, except this is a half of that. So we end up with mg L over 2 plus, yeah, over, it's like 1/2. I'm just, so much time. Okay, so, whew, yep. So what you have is this is the work done by gravity on the center of mass. This is the work done by friction. Go to that.
Yeah, it would have been quicker if you just added, if you would have realized that total, let's see,